So last time I told you that optimization comes in the form of word problems. So the thing that you have to do first is you need to read it carefully, and then you have to figure out what is your unknown, what is your given quantity, what is your condition, and then after that you're trying to construct a function in one single variable. Well, you're trying to maximize or minimize that function. Does it make sense? And then, well, the solution gonna be the one that solve the optimization problems. So in order to maximize or minimize the function, we're gonna use the calculus. So the method from calculus is when you have a function fx. This is a function of a single variable. So you need to make sure that you have a function of a single variable. And then after that, you can take the first derivative, right? And then set it equal to 0. So when you take the first derivative and then set it equal to 0, you can solve for max and min. Well, that usually it's a basic strategy for this topic. All right, we have about 30 students now, so let's get started. So we're gonna look at 2 more examples. So example 102, this is what we did last time. So I just show you how to use calculus to maximize the area of the field. Well, and you can see that on this example, we have the constraint that the length of the fence is 500. So let's do 2 more examples. So example 103, let's suppose that we have a piece of a cardboard that is 50 centimeters times 20 centimeters. We are going to cut the corner and fold up the side to form a box. So we want to find the height of the box that will give us a maximum volume. So if you look at the picture here, so you have a cardboard that one side have a length 50 and another side have a length 20. And what are we going to do is we are going to cut the cardboard like that. The one that I just draw the purple line here. And then once I cut the cardboard like that, so I'm gonna fold it up to get a box. And when you get a box here, you can compute the volume, right? So the volume gonna be just width times length times height. That's going to be our volume. So you can see that for here, you can define this problem into some mathematical notations, and then you can solve for the maximum. So the idea is we are going to let the length of the corner that we cut out here to be h, right? Because this is going to be our height at the end, right? So when we cut the corner with the length h, so at the end when we fold it up, so this is going to be our h, right? Just the height. So if I cut off on the 2 corner here, so I'm gonna cut off h and h. So that means in the middle here, I'm gonna have 50 minus 2h, right? And then if I cut out this thing to be h, cut this thing h. So in the middle, I'm gonna have 20 minus 2h. So, well, we're gonna start the problem by let h be the height of the box. So when we get the height of the box, so we can see that the volume of the box is going to be width, which is going to be 20 minus 2h. And then this is going to be our width for the box here. This is going to be 20 minus 2h, sorry. This is 50 minus 2h, right? You can imagine that you fold the box up and then that will be your width and length. So the volume of the box going to be 20 minus 2h times 50 minus 2h and then times h. Right. So this is actually going to be your volume of the box, and then you can multiply them together. So this is going to be well, I need to do the multiplication, so I have no choice. So this is going to be 1000 and then minus 140h and then plus 4h squared and then times h. So at the end, I'm going to get 4h cubed minus 140h squared and then plus 1000h. Well, this is going to be my function for the volume of the box. You can see that this is good because we have a function in terms of a single variable h, right? So this is going to be my function. So the idea is we want to maximize this function. We want to maximize v. Well, technically, this is going to be the hardest step for optimization problem. You need to read the problem carefully and try to manipulate the problem in terms of mathematics. Once you get a function of a single variable up to this point, the rest of the work is easy. You just need to follow your calculus. So I'm going to differentiate one time. So I'm going to get 12h squared minus 280h and then plus 1000. And then after that, I need to solve for h, right? Because the critical value or critical number is going to happen at the point that the first derivative is equal to 0. So I can set the first derivative to be 0 and solve for it. So how do I solve 12h squared minus 280h plus 1000? So for sure, well, remember, if you have ax squared plus bx plus c equal to 0, and you feel like you do not want to factor it, so you can solve it by x equal to negative b plus or minus b squared minus 4ac, right, over 2a. This is a solution for the second degree polynomial, right? You can see that for this problem, I have a equal to 12, b equal to 280, b equal to negative 280, c equal to 1000. So I'm going to solve this equation, and that will leave me h equal to negative 280, and then plus or minus square root negative 280 square minus 4 times 12 times 1000. And then over 2a. So 2 going to be here, and then a is 12. So you just plug in all the numbers, and then you're going to get 280 plus or minus square root something, which I'm going to give you the final answer because I already did this thing at home. So, well, after I simplify everything, so I'm going to get 35 plus or minus 5 times square root 19 over 3. So suppose I cancel everything and then I get the final answer here. So I don't want to waste time to cancel the numbers here. So I did it beforehand. Well, once you get h equal to that, so that means now you have to figure out what is going to be your answer. H equal to 35 plus 5 square root 19 over 3, or h equal to 35 minus 5 times square root 19 over 3. So you have to answer here. However, you can see that. So we can see that the value of h, must be in between 0 and 10. How do we know that h must be between 0 and 10? This is because you can see that the width of the box is 20, as I highlight in green, right? And then if I want to cut 2 corners of length h, so the maximum of number of h must be 10, right? Because if I use h equal to 10, it means, yeah, you just cut half 20 to 10 and 10, right? It is impossible that you're going to get the number h that is bigger than 10. So which imply that your function h, I mean your value h must be 35 minus 5 times square root 19 over 3. It cannot be plus, because if it is a plus, then your h gonna be bigger than 10, and that is impossible for this problem. So this is going to be my h. So if you use your calculator, this is going to be 4.4018 approximately. So this is going to be our critical value or critical number. Does it make sense? So once you get your critical number, so this is going to be the one that gives you, it is your candidate for maximum or minimum, right? So to make sure that you have a maximum, you can take derivative one more time. So this is going to be 24h minus 280. And you can see that when you plug in the number 4.418, so this is going to be 24 times 4.4018 minus 280, which is going to be a negative number, right? So that means 4.418, 4.4018 here give us the maximum. Well, I ran out of space, but well, it gives us a maximum because the second derivative is negative, right? When the second derivative is negative, that means at that point you get a maximum. So the answer is going to be h equal to 4.418, 4.4018. Does it make sense? Well, on the exam, you need to explain that. Well, this is enough for, I mean, if this is a problem on the exam, so this is enough for the full credit. But, well, I will answer the question in the chat. So Sirapop asks us that why can't h be more than 10? Because you can think of that, well, I will say it again one more time. You look at the one that I highlight in green. So the one that I highlight in green here, this is of length 20. So we're gonna cut the corner to be h, right? If I let h to be more than 10, this is impossible because the total length is just 20. So that means it forces us that h must be between 0 and 10. Sounds good? So the maximum situation, I mean the extreme situation, is you let h to be 10. If you let h to be 10, then boom, then you get the 10 plus 10 is 20. So that means you didn't leave the length for the other side. So that is why h must be between 0 and 10. That hopefully that answers your question. And then from Pimapon, do we have to explain why h must less than 10 in our solution? Well, you don't have to. For this one, you don't have to. Well, if you say that, we can see that h is between 0 and 10, that's fine. But if you want to explain, that's even better. But here, if you say h between 0 and 10, fine. But if you do not state that h must be between 0 and 10, you just pick your answer randomly. So, well, for sure, you're going to lose some credit because you didn't say anything. But, well, you need to say a little bit that, okay, h must be this number, something like that. Do we have the top of the box? Well, we don't, right? Because this question didn't say anything, but even we have the top of the box, who cares, right? Because the volume gonna be width times length times height anyway, right? Does it make sense, Puvin? Because the volume doesn't change at all. I mean, even we have a top of the box or not. So this is the example for optimization problem, and you can see that the problem is so complex because you need to read the problem carefully and then just translate everything in terms of mathematics first. Sounds good? All right, so if you still are not comfortable with optimization problem, we're gonna do one more example. and then we're going to move to the next section. All right, so let's do one more example here. So I'm going to look at example 104. This is the hard one. Well, let's see if you can do this one. Well, I'll show you here together, but if this show up on the exam, this is supposed to be the A level, the hard one. So let's say, suppose we have a rectangle metal sheet with perimeter L units. So our goal is to roll the metal sheet to a cylinder with no top and no bottom. So use calculus to solve for the dimension of the rectangle metal sheet that maximize the volume of the cylinder. So the idea is you have the metal sheet and then you want to roll it to the cylinder. Does it make sense? So when you roll it, so you're going to get a cylinder. So you just put one side and one side, just roll it and just attach together. So you're going to get a cylinder. So the question asks us that, well, if you know that this is L, the perimeter is L, what is going to be the dimension that maximize the volume of the cylinder? You can see that the hardest part for this question is you didn't see any number. This is just, they just give you L, that constant, right? And then they ask you to solve for the dimension that maximize. So the hardest part is how do you set up the problem? So I'm gonna let X and Y to be the length of two sides on the metal sheet, of the metal sheet. So I'm gonna let X and Y to be the length here. So I'm gonna let this to be X, X, Y, Y, right? So what is given is, you know that the perimeter is going to be L units. So that means X plus Y plus X plus Y equal to L, right? Because it is given that the perimeter is going to be L units. Well, in other words, X plus Y equal to L over 2. In other words, L equal to L over 2 minus X. Sounds good. So when we roll it to the cylinder, so we're going to get a cylinder here. And the cylinder, for what is the formula for the volume of the cylinder? So the volume of the cylinder is going to be pi r square times height. Does it make sense? Because, well, this is going to be the volume, the formula for the volume. However, well, the height that you're going to use here, h, this is going to be the same thing with y, right? If you look at the picture, right, you can imagine that the volume v going to be pi r square times y. Whoa. Sounds good? Well, you can see that from the picture, the volume of the cylinder is V equal to pi r square times y. And then, well, the goal is, this is the formula for the volume. However, it must be a function of one variable, right? Because if it's a function of one variable, you can differentiate and find the point that gives you a maximum. However, so this is a function of two variables, I and y. You have to switch it into a single variable here. So how could I do that? So you can see that, well, we have y equal to L over 2 minus x. So I can switch y to L minus 2 over x. And what is your r here? So your r going to be the radius here. So you can see that on this side x that I highlight in yellow. So you can roll it and then you're going to get a circle with radius r. So from the picture, we also know that, well, 2 pi r, right? 2 pi r, this is going to be our circumference of the circle. Well, this is equal to x. Because you have x here, and then you're going to roll it to, the circle, right? So that means 2 pi r equal to x, well, which means r equal to x over 2 pi. All right, after that, well, you have everything that is ready to compute derivative. So I'm going to start by v equal to pi. Well, you replace r by x over 2 pi. You replace y by l minus 2, l over 2 minus x. And then now you can differentiate, right? Because everything is in terms of x now, you can differentiate. And then once you differentiate, one time set it equal to 0, then you're going to get the point that give you maximum. So this is going to be, well, pi times x squared over 4 pi squared, and then multiply l minus 2, or l over 2 minus x. Well, this is 1 over 4 pi, right? Because I cancel the constant. And then I multiply x squared there. So I'm going to get l x squared over 2 minus x cubed. Here we go. So I have v here. So I'm going to differentiate one time with respect to x. So I'm going to get 1 over 4 pi and then differentiate l over 2 x squared. So I get x, right? And then differentiate 3x squared, I get, well, I get lx, sorry. I get lx. And then after that, I get 3x squared. Well, if I simplify a little bit, so I pull out x. So this is 1 over 4 pi times x times l minus 3x. Well, this is my first derivative. Well, v prime equal to 0 if x equal to 0 or x equal to l over 3, right? Because you have v prime equal to 1 over 4 pi times x times l minus 3x. So in order to get the 0 here, so it must be the case that x equal to 0 or l minus 3x equal to 0, which means x equal to l over 3. Well, you can see that x equal to 0 is impossible because, well, it does not make sense to say that the length is equal to 0. So x equal to 0 is impossible. So your answer for the critical number is going to be L over 3. This is your critical number. And once you get your critical number, so how do you know that gives you a maximum? So you can differentiate one more time. So I'm going to differentiate V one more time. Well, this is going to be 1 over 4 pi. Well, differentiate Lx, so I get L. Differentiate 3x squared, I get 6x. Well, and then you can see that V double prime at L over 3. This is going to be 1 over 4 pi times L minus 2L, which is going to be a negative number, right? Well, that means the maximum is at 10. So that means the maximum is at 10 at the point x equal to L over 3. Sounds good? So the answer is, well, I will leave the answer on the top here. So which is, the answer is the design dimension. So the dimension that we want is going to be x equal to L over 3 and y equal to L over 6. Because once you get L over 3 here, you can solve for y, which is L over 6, because y equal to L over 2 minus x. All right, any questions? So one question from Sirapop, we can treat L as a constant, right? Yes, because the number L is a constant here. So we can treat L as a constant. So this is a problem that show you the hard one. Well, this takes time for you to follow each step and compute the first derivative and then set it up equal to 0 and then show that this is a maximum. So any questions up to this point? Well, if not, we're going to move to the next section. So we have completed the section 5.1 now. So for those of you who are in today, let's check in. I just want to check who is in today, because so type in the chat that you are in today, because I want to see that there is a relationship between the person who attend class and the midterm score. So maybe, okay, sounds good. Well, before we move to another section, so let's look at practice problem here. Again, well, because we don't have time to show you a lot of examples for this class, I want you to do practice problem first. Once you do the practice problem, so I'm gonna post a solution online on my YouTube channel. So example 105, 106, 107, and 108. This is the example to make you practice on optimization problems. So if you wanna sharp your skill, so you can try to do all of this. So 105, 106, 107, 108. The difficulty is not that hard compared to the previous example. So I hope you find, I hope you can find the, I hope you can practice a lot. So I lost my mind because I read the chat. Okay, so yeah, example 105 and 108. So I will do this. I will show you the solution on my YouTube channel later. So this is the practice problem set number 2. We have the practice problem set number 1 from Monday too. So the solution, for example, 98, 98 to 101, and also 105 to 108 we will post maybe this weekend, because I just need to record it pretty soon on my weekend, I think. All right, so before we move to section 5.2, let's look at the chat first. Okay, I have one question. Where can I get this slide? Well, you can go to Blackboard and download the slide from TikTok from the section 52 folder. So they're gonna have a section. Well, once you log into Blackboard, you're gonna see the section 52 folder, and you're gonna see the blank lecture note there. So you can download my lecture note over there. So everything from our section 52 gonna be posted on that folder. Well, I have the YouTube channel there. Well, the link to the YouTube channel, and also the blank lecture note, and also I'm gonna post annotated lecture note after class, maybe a few days after class. All right. Anything else? All right. No questions about 35 student year. Sounds good. So we're gonna move to section 5.2. So this supposed to be the new one for you. So section 5.2, this is the section we are talking about concavity and inflection points. So for this section, we're gonna learn what does the second derivative tell us about the function f. So we know a little bit that the second derivative helps us in terms of the second derivative test. You can check that the critical number gives you local maximum or local minimum by using the second derivative test. So what else we can conclude from the second derivative test? So you can imagine that when you have an increasing function, as you see in the picture here, when you have an increasing function, you could have an increasing function in 2 ways, like figure A or figure B. Sounds good? So you can see that, well, they are different. So the situation in figure A, this is called concave up. The situation on figure B, this is called concave down, right? So this is on figure A, this is called concave up or concave upward. So this picture on the right, that is the case that is called concave downward, or just concave down in short. So definition. So if you have the graph of f, so if the graph of f lies above all its tangent line, that means the function is concave up. This is going to be the case that you see on the left hand side of the picture here. So you have a function f, and then you can see that all the tangent line is just below the curve. So if you have the function that is increasing like that, the one that I highlight light blue, but the tangent lines all above the real curve, that means the function is called concave down. I don't know if you have a hard time to memorize this thing, but when I was a kid, this is how I memorized. So I'm gonna memorize that. Well, concave up. This is going to be smile. For concave down, this is going to be sad. This is how I conclude when I was a kid. So concave up, you get the graph like that, smile. So when concave down, you're gonna get the graph like the sad one. So that is the definition of concave up and concave down. So it is possible that sometimes you're gonna see the function that is increasing, and then it switch from the concave up to concave down, something like the sigmoid curve. Have you ever seen something like this is going up, and then at some point it's just going up again, but it just changed the concavity. So at the point here that they change the behavior, like this is the point x equal to a, and then you can see that on the left hand side of the point x equal to a, this is called concave up, right? Because the graph it just look like the smile thing, so this is concave up, and then the right hand side, this is called concave down, right? Well, if the graph switch from concave up to concave down, at that point, this is called the inflection point. So this is the point that the concavity switch from one thing to another thing. Does it make sense? So and then how do we know that the function is concave up and concave down? By looking at the equation, not from the picture. Okay, if I give you a picture, it is easy, right? Because you can look at the picture and figure out this is concave up, this is concave down. However, when you get the equation, the thing that gonna tell you about the concave up and concave down is the second derivative. You can see that the case of the concave up, you're gonna get the slope that is getting bigger as x increase. You can see that your slope is getting bigger and bigger. So as x increase, if your slope is getting smaller and smaller, so that means the function is concave down. So and the slope is the first derivative. So that means concave up means the second derivative is positive. So concave down means the second derivative is negative. So we have a theorem say that, well, if the second derivative is positive, then the function is concave up. If the second derivative is negative, so the function is concave down. Again, I would suggest you to memorize that. Hey, the concave up, this is the case that the function going like that, like that. So the concave down, this is the case of function going like that, or like that. Right? This is, well, the first one that I highlight in green now here. This is the decreasing function and concave up. Here, this is a function that increasing and concave up. This is the one that increasing and concave down. This is the one that decreasing and concave down. Sounds good. So the thing that you have to carry to the next step is, well, remember like that, the first derivative tell you increasing or decreasing. The second derivative tell you concave up or concave down. We're gonna put everything together and plot the graph at the end of this class. Sounds good? All right, so let's do few examples about concavity first. And then we're going to show you how to plot the graph by looking at the equation. All right, let's look at two small examples before we get to the graph section. Example 109. Well, I want you to find the intervals where the function arctan x is concave up or concave down. All right, so let's look at the example 109. So for sure, if I want you to find the interval of concave up and interval of concave down, you need to differentiate 2 times because you want the second derivative. So I'm going to have fx equal to arctan x. So the first derivative is 1 plus 1 over 1 plus x squared. This is the first derivative. Well, this is actually 1 plus x squared to the negative 1. Right? And then I take the second derivative here. Well, that means I'm going to get negative 1 times 1 plus x squared raised to the negative 2. And by the chain rule, I have 2x. Well, this is actually negative 2x over 1 plus x squared over 2. Well, the reason why I switch 1 over 1 plus x squared to 1 plus x squared to the negative 1, because I want it to easier to differentiate. And then after that, I need to figure out the sign of f double prime x. Right, this is f double prime x. So what is the sign of the f double prime x? So for sure, 1 plus x squared over everything squared, this is always positive. Right? This is always positive because this is the square thing and the thing inside parentheses is positive. So you only have 2x on the top here. So the cutoff point is going to be number 0, right? So when x is bigger than 0, that means 2x is going to be positive. Well, negative 2x over 1 plus x squared. This is going to be negative. So this is negative. And then on the left-hand side of 0, so when f is negative, well, your second derivative of f is going to be positive. Well, we're going to call this thing number 0 inflection point, right? Because this is the point that the concavity switch from plus to minus. Well, on the left-hand side here, you have concave up property. So this is on the right-hand side here, you have concave down. I have the concave down property. So 1 second, I need to shut down Siri. Okay. Concave up and concave down here, and then so I get the interval of concave up. This is going to be negative infinity to 0. And then the interval of concave down, this is going to be 0 to plus infinity. Well, and if you just looking at the graph of arctan x, it does match with the property of the concavity, because the graph of arctan x is like that. Sure. This is y equal to arctan x. So you can see at that below, at the point below 0, x less than 0, it is concave up. And then it switched to concave down after 0. Well, some of you are going to be worried about the interval here. So I use the open interval here. But, well, at the point 0, it doesn't matter that you're going to include it or not. Well, because it depends on the book you read. Again, it depends on the book that you read. So some books going to use open interval. Some books going to use closed interval. It depends on the book you use. But here, I am going to use the open interval. But what if you use a closed interval here? doesn't matter. So you still get full credit. If you use the closed interval, it doesn't change your idea at all. So, well, that's what I want to say. So if you want to look at the inflection point, this is going to be just 0, 0. Right? Because when x equal to 0, y equal to 0, and that is the inflection point for arctan x. Sounds good? All right. We're going to do one more example, and then we're going to look at how to sketch the graph. That is going to be the fun one for today. All right. Example 110. So stay with me, please. So we're going to learn about, I think, 40 minutes more, and then we can stop. So example 110. Here I have fx equal to x cubed minus 3x squared plus 2. So I want you to use the calculus again to answer the following questions. Well, this could be a good candidate for the exam. So this is supposed to be the easy one. I want you to find the interval of increasing and decreasing and find the local extreme value if exists, and also find the interval of concave up and concave down. Inflection point if it exists. All right, so let's do it. We have fx there, so we're going to differentiate one time. 3x squared minus 6x. Well, this will give you increasing, decreasing properties. Again, I pull out 3x. I have x minus 6. Oops, no, x minus 2. Okay, good. Well, and then I have f double prime x to be 6x minus 6. Well, this is 6 times x minus 1. All right, let's start from question A. So what is the interval of increasing and decreasing? So you have to look at the critical number, right? So f prime x, this is 0 when x equal to 0 and x equal to 2, right? So that means, well, you can figure out the sign here to be plus, minus, plus. Well, you can try it at home. So if you pick any number between 0 and 2, so you're going to get f prime to be a negative number. Once I get a sign here, so that means I can answer the part A. So part A, the interval of increasing. This is going to be negative infinity to 0, union to infinity. Well, that's the interval of increasing. And the interval of decreasing, this is going to be just 0 to 2. All right, for part B, if I want to find the local extreme value, so you can see that this is increasing and then decreasing and then increasing, right? Well, which means you know that at x equal to 0, at x equal to 0, the local maximum is attained. Well, which means at the point x equal to 0, you have a maximum. So when x equal to 0, you get f0 equal to 0 cubed minus 3 times 0 squared plus 2. This is 2. So f0 equal to 2. So this is your maximum value. All right, and then at x equal to 2, this is the local minimum. Right, the local min gonna attain the function f has local minimum at x equal to 2. So you can compute f2 here. So for those of you who can do this thing, you're gonna think, oh, this section is so easy and simple. Well, I am happy that you think that this is easy and simple, because this is the easy one for the final exam. To raise to the third power, so 2 cube is 8 minus 12, right? And then plus 2, negative 2. This is the minimum value. All right, A and B are easy like that. So let's do part C. So part C, we're talking about concave up and down. So F double prime here. So the point that is a candidate for inflection point is going to be just x equal to 1. And then once you figure out the sign, this is going to be minus and plus. So, well, the interval of concave up, this is going to be 1 to infinity. As I told you, it doesn't matter, use open or close interval. It depends on the book you use. The interval of concave down, this is going to be negative infinity to 1. All right, so part D, the inflection point is going to be, well, the concavity change from concave down to concave up at x equal to 1. So when x equal to 1, we have the inflection point. When x equal to 1, that means, let's say 1 cubed minus 3 times 1 square plus 2. So that is 0. So it's going to be 0. Right? So the inflection point is 1, 0. Sounds good? All right. Any questions? Any question? All right. All right. Hopefully you feel like this is doable and this is not that hard for you. Well, this is supposed to be the easy one on the exam. All right. Next, we're gonna move to the last section. Well, not the last section. So this is going to be a big section for you, curve sketching. This is going to be a huge part of the final exam. So if you skip this part, you're going to lose about, oh my God, I mean, I think more than 10%. Well, this is a big question and big one. Let's say, suppose, well, I answer the question in the chat first. So we have a question that domain F does not include 1, then the answering 1 to infinity. Well, for sure, if the domain F does not include number 1, you just exclude number 1. Well, that's pretty simple. That's pretty simple that you just exclude number 1. Well, if the domain does not include number 1, you just exclude it. So the interval of increasing and decreasing, the interval of concave up and concave down, well, it doesn't matter that we argue about it closely. And I mean, it makes no sense to discuss about what should we include uh, the critical number or not? Because, you know, well, when we talk about the interval increasing or decreasing and interval concave up, concave down, we only care about the interval, not just the extreme point. I hope that helps. Okay, we're gonna look at the curve sketching. So the goal for today is I want to do at least one example. So I think it's only just one example because we don't have much time left. But we're gonna do just one example for curve sketching. And this is going to be a beautiful section. So you can, well, it's gonna test you everything. So it's a time to put everything together and sketch the graph. So, well, of course, nowadays we have a calculator, we have an internet. You can just plot any graph in just few seconds. Just put it in Google and then it's going to graph it for you. But what are we going to do is we're going to take a step back and we're going to look at how to tell the behavior of the graph and sketch the graph without using any technologies. Well, for sure, in real life, it is possible that you will not have a chance to use the technique from this section, but we just learn how it develops in mathematics. Does it make sense? So on the exam, you are not allowed to use a calculator. So that means if I ask you to sketch a graph, you have to start from the scratch. Let's look at the guideline. So in order to sketch the graph, this is going to be our the section that it's like an art. So you need to find the domain. the intercept. Well, sometime range. Well, sometimes if you get the range, it is maybe useful as well. And then you need intercepts. You need interval of increasing, decreasing. You need local max, local min. You need interval of concave up, concave down. You need point of inflection, and also you need asymptotes. Once you have everything here, you can put everything together and plot the graph. I'm going to show you the real example in 5 minutes. But before we look at the real example, so let's look at the behavior of graph first. So it is possible that you're going to have the 4 types of curve. The first one that I highlight in light blue, this is the one that you have increasing function and concave up. So if you have increasing function and concave down, it's going to be like the one that I highlight in yellow. If you have decreasing function and concave up, going to be the one that I highlight in green. And the last one, if you have decreasing and concave down, it's going to be that I highlight in orange. So that is the 4 types of the curve. All right. Before we look at the real example, we already learned interval of increasing, decreasing, local max, local min, interval concave up, down, point of inflection. We learned all of those things. So domain, this is easy because we learned domain and range just from the high school. So the domain is the possible value of x that you can put into the function. And then the intercept is also easy. The intercept is, well, if you want to find x-intercept and y-intercept of the graph, you just need to let one variable to be 0, right? If you let x to be 0, then you get y-intercept. If you let y equal to be 0, then you get x-intercept, all right? But for asymptote, this is maybe new for you. So asymptote is the one that well, we're gonna have 2 types of asymptote for this class, which is called vertical asymptote and horizontal asymptote. So the vertical asymptote is the one look like the line x equal to a here. So this is the point that the line that give you a vertical line here. So the behavior of the vertical asymptote is the one that when you take limit of the function, it's go to infinity. So you can see that the one that I highlight in green here, if I take the function, take the limit of the function f, where x go to a. So no matter what answer is, plus or minus infinity, we're gonna call it vertical asymptote, right? Because sometimes you're gonna have the pattern that, hey, when x equal to a, Ajahn, I got like something like that. Well, a is called vertical asymptote too, because well, the graph just approach plus or minus infinity at x equal to a. This is called vertical asymptote. How do you find vertical asymptote? So the vertical asymptote is the one that usually is the one that the denominator equal to 0. That is the vertical asymptote. So denominator equal to 0. For example, if you have fx equal to 1 over x minus 3 here, so that means x equal to 3. This is your vertical asymptote. Well, the point that gives you denominator equal to 0, that one gonna be the vertical asymptote thing, right? Because if you know that the denominator equal to 0 and your numerator is just a number, so when you take limit, you learn the limit section already. The limit is going to be plus or minus infinity. So that means the vertical asymptote is the one that will give you the denominator equal to 0. For horizontal asymptote, this is the one that you take limit, go to infinity or go to negative infinity, and then you get a real number L. This is called horizontal asymptote. So the picture is going to be something like here. You have y equal to b. This is going to be your horizontal asymptote, because when you take limit go to infinity, the function just get close to y equal to b, right? The value of y just close to b. So this is called the horizontal asymptote. Make sense? All right. Any questions so far? All right, it's 4 p.m. now. Yeah. So let's do one example and then we can go. So we're gonna do example 111 together. Well, this is going to be the big one. Well, it should take about 15 minutes to do this one, and then after that, well, the class dismissed. So let's do this one together. All right, any questions before we get started? All right, so let's look at how fun it is. So well, I told you this thing, everyone listen to me. So on the exam, well, we're gonna ask you to graph the function. I will give you just a function like that. And then you have to graph it. At the end, we're gonna ask you so many questions here. And then at the end, we're gonna ask you to sketch the graph. Well, you can see this is a big question because we can ask like a lot of things. Supposed to be about, well, so one question may be 10 points on the exam. So well, if you choose to skip, well, the big chunk gonna be disappear. So make sure that you can do some graphing, sketching technique problems. All right, so let's look at number one. So the domain, what is the domain here? So the domain for sure is going to be real number, right? Because it can be anything. So X can be anything. So the domain, you're gonna have a problem of the domain when you have the denominator equal to 0 or something like under square root. You just need to be the non-negative thing under square root or something like that. But because this is just polynomial, so no problem with domain. So it's going to be all real number, real line. And then x-intercept and y-intercept. So for x-intercept, let's look at that. For x-intercepts, you can let y equal to 0. So if you let y equal to 0, so you're going to get x to the fourth power minus 6x squared equal to 0. Right? So that's mean x squared times x squared minus 6 equal to 0. And then you solve for x, so you're going to get 0 plus or minus square root 6. Well, which means my x-intercepts going to be square root 6 and 0. 0, 0. And then negative square root 6 and 0. This is my x-intercept. And for y-intercept, I can let x equal to 0. Well, that means 0 to the fourth power minus 6 times 0 square equal to y. So y going to be 0. So 0, 0 is just also y-intercept. So this is all for the intercept. So you have two things now. All right, next, I want to find vertical asymptote and horizontal asymptote if exists. So you can see that we have no vertical asymptote. Right? Because this is a polynomial and then we don't have a problem with the denominator or something. So fine. So we don't have the vertical asymptote, right? And also we don't have a horizontal asymptote. Right? So the next example, we're gonna have a problem with asymptote. But for here, we don't have, because if you take limit of fx, where x go to plus or minus infinity, well, this is gonna give you plus infinity. So it doesn't give you something like a real number L. So no horizontal asymptote, right? All right, so number 4, let's compute the first and second derivative. So the first derivative is going to be 4x cubed minus 12x. The second derivative is going to be 12x squared minus 12. All right, so those are first and second derivative. So to make it more clean, so I am going to simplify a little bit. So I'm going to simplify the first one to be 4x times x squared minus 3. I pull out 4x. The second one, I'm going to pull out my 12 just to make it cleaner. All right. So I have that. So the question number 5, I want you to find the critical numbers and the interval of increasing and decreasing. So if you look at the behavior of f prime, so you can see that our critical number is going to be the point that f prime x equal to 0, or which means 4x times x squared minus 3 equal to 0. So this means x equal to 0 plus or minus 3. Well, this means 0 square root 3 negative square root 3. So this is going to be your real line, right? And you can try to put the sign here. So I'm going to get plus, minus. So if you don't trust me, you can try to put any number in between those interval, that interval, into the function f prime. And then you're going to see that, hey, let's say x equal to 500. So if you plug in that, you're going to get f prime to be positive. If you plug in x equal to 1, so you're going to see that f prime is negative, and so on. So it's going to be plus minus like that. So our critical numbers are 0 plus or minus 3 and interval of increasing. Well, I just use abbreviation here. So this is going to be, well, I don't have to because we have interval of increasing is negative 3 to 0 union negative square root 3 to 0 union square root 3 to plus infinity, right? And interval of decreasing, we almost there, everyone. This is negative infinity to negative square root 3 union 0 to square root 3. All right, sounds good. Next, we're gonna look at the local max and local min. So local max and local min is what? Because we have minus plus here, so well, we can see that at the point x equal to 0, this is going to be the one that the function change the sign, the f prime sign from plus to minus. So this is going to be our local max, right? This is going to be our local min. I mean, the point that gives you local max, and this is the point that gives you local min. Something like that. So the local max gonna attain at x equal to 0, y equal to 0. The local min gonna attain that x equal to square root 3 and x equal to negative square root 3. So what is going to be the value when x equal to square root 3 or plus x equal to negative square root 3? So you can compute f square root 3, which is going to be square root 3 to the 4th power minus 6 square root 3 square, and that will give you 81. 81. Oh no, 9 times 9 is, okay, that's 3 times 3, this is 9, minus 6 times 3, which is negative 9. So which is negative 9. So now you have that local max is 0, 0. Local min is at square root 3 plus or minus square root 3 negative 9. All right. Next, we are going to look at the concavity. Almost there, man. Find the interval of concave up and concave down. All right. So from the previous slide, we have f double prime x to be 12 times x squared minus 1. This is going to be 12 times x minus 1 times x plus 1, right? And then when you draw the line here, you're going to have negative 1, 1, and then plus, minus, plus, and then, whoa, interval of concave up. This is going to be negative 1, negative infinity to negative 1, union 1 to infinity, right? And then interval of concave down. This is going to be negative 1 and 1. All right. Number 8. Are there any inflection points? For sure, we have inflection point, which is both of two numbers here. They are all inflection point. So inflection point, this is the point that we switch from concave up to down or down to up. Inflection point are negative 1 something and 1 something. So that means I have to plug in F1 here. So it is 1 to the 4th power minus 6 times 1 square. So which is 1 minus 6. This is negative 5. All right, so I have everything. Everything is ready to plot the graph. So this is how I plot the graph. So different book gonna use different technique, but I think this is the one that easy to do, and I usually use this one. Okay, let's do that together. So the last 5 minutes here. All right, I'm gonna draw the line F prime. I'm gonna draw the line F double prime in the same graph, and then, well, I'm gonna look at the line of F prime, and then you can see that the line of F prime here, I have the critical number negative square root 3, 0, and negative square root 3. So I'm going to put it here. So I'm going to have 0, negative square root 3, and square root 3. And then on the line of F double prime, I have negative 1 and 1. So I'm going to include everything together. So it's going to be negative 1 and 1. Negative square root 3, and 0. Here, what I'm going to do is I am going to put the sign over there. So you can see that for the graph of f prime, so it's going to be plus and minus like that. This is plus. Well, from 0 to negative, from 0 to square root 3, this is minus, right? And then from negative square root 3 to 0, this is plus, and this is minus. Because the sign of f prime switch like that. And then also the sign of f double prime, this is going to be plus or outside 1 and outside negative 1. Everything else is minus. Whoa, because that is the sign of f double prime. And once you get everything, so you can see that on the first interval from negative infinity to negative square root 3, the graph going to be decreasing, and also concave up. So this is like that. On negative 3 to negative 1, negative square root 3 to negative 1, increasing and concave up. This is increasing and concave down. This is decrease. This is decreasing and concave down. This is decreasing, concave up. Right, and the last one is increasing and concave up. So you know the pattern of the graph for each section times to put everything together. All right, so let's look at that. So when you put everything together, I'm going to draw the line first. Oops, sorry. Gonna down that. Y, X. All right, first we're gonna put the intercepts. Well, my intercept is -6, square root 6, and then negative square root 6, right? So I'm gonna put the intercept here. I have 0, 0 here. Square root 6 is about 2 point something. So 1, 2, 3, 2 point something here, square root 6. -1, -2, -3. So here it's just negative square root 6, 0. This is my intercept. And then I know that, hey, I have the local maximum at 0, 0. This is my local maximum. I have the local minimum at negative square root 3, -9. So this negative square root 3, which is negative 1.7, it's about this one. This is going to be my local minimum. This is my local maximum. And then also I have this point. This is also square root 3 and -9. This is also local min. So I'm trying to plot everything first, and then I'm gonna just connect the graph after. So I also have the inflection point, which is -1 and 1, right? And y equal to -5. So when x equal to -1 and -5, this is inflection point, and 1 and -5, this is inflection point. And take a look. Okay, first from negative infinity to negative square root 3, the function going concave, decreasing concave up, the graph gonna be like that. The one that I highlight in green, right? So it's gonna be like, well, up to this point, it must be like that all the way to this point. Concave down, but concave up, but decreasing. So the next one from negative square root 3 to -1 must be increasing and concave up. Okay, increasing, concave up. Oh, a lot easier like that. Next square from -1 to 0, increasing, concave down. Okay, increasing, concave down. Next, from 0 to 1, it's gonna be like decreasing, concave down, right? And then also the last one, the last two gonna be decreasing, concave up, increasing, concave up. Okay, and the last one must be increasing, concave up. Well, but it need to pass square root 6 here. Well, this is going to be the sketch of the graph fx equal to x cubed minus 6x squared. Well, if you put it on in Google or Mathematica or whatever, well, this is going to be the graph that you're going to get. Well, and we know that the graph going to be like this by using just calculus. And then you can see that, hey, this is local min, right? This is local max. And also this is going to be the inflection point, the point that it changed the concavity. So this is your first example. You may think, oh, Ajahn, this is so hard. This is just takes so many steps. But well, once you practice again and again, well, you see that this is super easy. So I like this section a lot. This is easy section because everything is just follow the step. All right, we're gonna stop the lecture here at slide 32. And next week on Monday, we're gonna continue doing more on sketching graph. Like we have so many examples here. So we're gonna try to show you so many different graphs and how to plot it by using just the properties from calculus. All right, before you go today, any questions? Well, we just lecture for, oh my God, 80 minutes for today. All right. Any questions, Cap? Well, some of you already left. Okay, sounds good. Anything else? All right, if you don't have any question, you can go. But if you have question, you can open the microphone or ask something in the chat. I'm just curious what the third derivative tell us about the graph. Whoa, 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 whoa.